Hello, welcome to today's class, and here we will deal with the new type of numbers, new type of variables. Those are known as complex variables. Before directly moving towards complex variables and their algebra, let us see how the complex numbers have originated. For example, let us look at the equation that is given here: x square plus 1 equal to 0. Now what is solution of this equation? That is, what is value of x? If we solve it, x square plus 1 equal to 0, it will become x square equal to minus 1. And what is x then? It will be equal to square root of minus 1. And what is value of square root of minus 1? It will be again root of minus 1. So it cannot be solved. So the controversy is that if such type of number is there, that is square root of minus 1 in the calculation, how the calculation will be performed? In other words, these are only the real numbers which are not sufficient. We have to consider some other numbers where there is a factor square root of minus 1 occurs. Later on, the symbol I is used for the number square root of minus 1. And in this way, what is square root of minus 4? It will be square root of minus 1 into 2. That means I2. What will be square root of minus 25? It will be square root of minus 1 into 5. That is I5 or 5I. In this way, a new kind of numbers, including symbol I, were introduced. Now, if it is 5 plus 2i, that means 5 is added to 2i, then it will be 5 plus 2i. So in this way, we have a new fashion of numbers, that is alpha plus ib, or I beta, for example, alpha plus I beta, where alpha and beta are the real numbers, and what is I? It is equal to square root of minus 1. Why we are dealing with such type of numbers in physics? Because in physics there are so many applications of such type of numbers represented as alpha plus ib in electricity, magnetism, elasticity, and most modern branch, that is quantum mechanics. So we must learn such type of numbers, that is alpha plus I beta, in detail. Now let us start with the definition of such type of numbers known as complex numbers. Now besides writing alpha plus I beta, I write here a number a plus ib, where what is I? It is equal to square root of minus 1. And what are a and b? A and b are real numbers. So a number of the form a plus ib, where I equal to square root of minus 1 and a and b are real numbers, is called a complex number. Now in complex number, a is real part and b is known as imaginary part. Okay, so a plus ib is a complex number where b is multiplied with I, and b, simply b, not ib, is called as imaginary part. while a is not multiplied with I, and this is a real number known as real part. So if it is a complex number, C equal to A plus IB, then A is called as real part of the complex number, and B, remember very well, not IB, B, simply B is called imaginary part. So it can be written like this, that A equal to real of C, or simply capital R in bracket C, or simply capital R's with subscript C. So it represents real part of C. And B, which is imaginary part of C, can be written as capital I subscript M C, imaginary part C. Capital I in bracket C, imaginary part of C, and I simply capital I subscript C. So it is imaginary part of C. So it is a fashion of how to write real and imaginary part of C. Now, the complex number C equal to A plus IB can also be written without using a symbol I, and it will be simply writing in the same way as we write the xy coordinates of some point in the xy plane, that is x comma y. Here we write C equal to in bracket A comma B. Okay, so C equal to A plus IB can be written as A comma B in simple bracket. Now what is A? If it is written to be in this fashion, then A is simply equal to A comma 0. Okay, that means A plus 0I. If it is to be written in terms of, or in the fashion of complex number, it is A plus 0I, or simply A plus 0 or equal to A. So A can be written as A comma 0. And what is B? It is 0 comma B, that means 0 plus BI, that means simply BI. So this is what? 0 comma B. And what is I? It will be simply equal to 0 comma 1. So 0 comma 1I, or 1I, or simply I. So I can be written in terms of ordered pair 0 comma 1. So in this way, C equal to A comma B is an ordered pair of real numbers A and B. This is such an ordered pair that A comma B is not equal to B comma A, and it is equal only in the special case when A is equal to B. Now how will you explain this? So A comma B, it is equal to A plus IB, where A is real part and B is imaginary part. And what is B comma A? It will be B plus AI, because first number represents real part and second number represents imaginary part. So in this way, if A is not equal to B, we cannot write that ordered pair A comma B is equal to B comma A. Generally, ordered pair A comma B is not equal to B comma A. Now up till we have considered real numbers A and B, let us consider variables x and y. In that case, we have a complex variable z equal to x plus iy, where x is real part and y is imaginary part of the complex variable z. In terms of ordered pair, it can be written as x comma y. Again here I is equal to square root of minus 1. Now let us look at the another property of a complex number, and that is known as modulus of a complex number. Modulus of a complex number is always positive. Remember very well, modulus of a complex number is always positive. And if it is a complex number a plus ib, it is defined as modulus of c equal to plus, put here plus sign always, it is always positive, plus square root of a square plus b square, or simply plus a square plus b square raised to or having power 1 by 2. So it is simply square of real part plus square of imaginary. So if it is c equal to a plus ib, the modulus of c, so it is written in this fashion, two parallel lines and in between c, plus square root of a square plus b square. Now if it is a complex variable z equal to x plus iy, then modulus of z is simply plus square root of x square plus y square, or plus in bracket x square plus y square bracket to the power 1 by 2. So this is a modulus of a complex number, which is simply square root of summation of square of real part and square of imaginary part of a complex number. And since it is modulus, it is always positive. Now let us see what is the condition that two complex numbers are said to be equal. Two complex numbers are said to be equal only when their real and imaginary parts are separately equal. Suppose we have two complex numbers, z equal to x plus iy and z prime or z dash equal to x prime plus I y prime. Now if z is equal to z prime, then x is equal to x prime and y is equal to y prime. In other words, z is equal to z prime if and only if x is equal to x prime and y is equal to y prime. Thus, two complex numbers z and z prime are equal if and only if their real parts x and x prime are equal and their imaginary parts y and y prime are equal. Since complex numbers or complex variables comprise of real numbers with imaginary number I, they obey all the rules of or all the fundamental laws of algebra. That means all kinds of algebraic functions, including addition, subtraction, multiplication and division, is possible for complex numbers. For this, we consider two complex numbers, z1 and z2. z1 equal to x1 plus iy1 and z2 equal to x2 plus iy2. Then what is z1 plus z2? It is equal to x1 plus iy1 plus x2 plus iy2. We can write it as x1 plus x2 in one separate bracket, and in the from the next two terms, that is iy1 plus iy2, we can take I common, so it will be I in bracket y1 plus y2. So in this way, z1 plus z2 is equal to x1 plus x2 plus I in bracket y1 plus y2. So we can define the sum of two complex numbers as a complex number whose real part is sum of the real parts and imaginary part is sum of the imaginary parts of the two given numbers. In this way, if Z1 equal to x1 plus I1 and Z2 equal to x2 plus I2, then what is Z1 plus Z2? It is equal to sum of real parts, that is x1 plus x2 plus I into sum of imaginary parts, that is 1. So, it is simply sum of real parts and sum of imaginary parts. So that is x1 plus x2 plus I in bracket y1 plus y2. That means sum of two complex numbers is a number whose real part is sum of real parts of the numbers and imaginary parts is sum of imaginary parts of the numbers. Now let us look at the different laws obeyed by the addition. All laws obeyed by the real numbers are also obeyed by the complex numbers. For example, the very first one is commutative law of addition. That means if there are two complex numbers Z1 and Z2, then we can write Z1 plus Z2 is equal to Z2 plus Z1, and we can prove this in a very simple way. So Z1 plus Z2, put here the value of Z1, that is x1 plus Iy2, and put the value of Z2, that is x2 plus Iy2. So we can write it as x1 plus x2 in one bracket plus I in bracket y1 plus y2. Now since x1 and x2 are the real numbers, they can be commutative towards addition. So x1 plus x2 can be written as x2 plus x1. Similarly, y1 plus y2 can be written as y2 plus y1. So in this way we have x2 plus Iy2 plus x1 plus Iy1, which is equal to z2 plus z1. So z1 plus z2 equal to z2 plus z1. That means commutative law of addition is obeyed by complex numbers. Now the next law that is obeyed by the addition of complex numbers, that is associative law of addition. Here we are making association of two numbers and we will add a third number. For example, Z1 and there is association of two numbers Z2 plus Z3. So Z1 plus in bracket Z2 plus Z3. It will be equal to, now Z2 and Z3 were associated, now here association changes and here it is Z1 plus Z2 associated together, that is written in bracket plus Z3. Okay, so Z1 in bracket plus in bracket Z2 plus Z3 equal to Z1 plus Z2 in a bracket plus Z3, which is equal to Z1 plus Z2 plus Z3. And it can be proved in a very simple way. Z1 plus in bracket Z2 plus Z3. Let us put the values of Z1, Z2 and Z3 as x1 plus I1, x2 plus I2 and x3 plus I3 respectively. And let us solve this. So simply x1, y1, x2, y2, x3, y3 are real numbers. Their association can be changed. So in this way, we can associate x1 plus I1 plus x2 plus I2 here, and we can separate x3 plus y3. And what is this bracket? That is bracket in bracket x1 plus y1 plus x2 plus iy2, x1 plus iy1 plus x2 plus iy2 is simply z1 plus z2. plus Z3. So in this way, Z1 plus association of Z2 plus Z3, it is equal to association of Z1 and Z2 plus Z3, which is simply again equal to Z1 plus Z2 plus Z3. Now, another law that is obeyed by addition of complex number is that there exists an additive identity. What is identity? When identity is functioned with the is used in with algebraic function, it doesn't make any effect to the complex number. And in this case, additive identity is found to be 0. Identity for addition of complex numbers is 0. That means when 0 is added to any complex number, there is no change to a complex number. It remains as it is. Thus, Z is a complex number, and if Z is added with 0, so Z plus 0, it is simply equal to Z, no change to Z. We can prove this in a very simple way. Let us write Z plus 0, which is equal to, now in case of, in terms of ordered pair, Z can be written as x comma y, and 0 can be written as 0 comma 0. So if we add, then we have addition of real parts and addition of imaginary parts. So x plus 0 comma y plus 0, and x and 0 are real numbers, so their addition is x. Y and 0 are real numbers, so their addition is y. So x comma y, which is again equal to 0, which is again equal to Z. In this way, Z plus 0 is equal to Z is proved. Another law is that there exists an additive inverse to a complex number, and the additive inverse of a complex number Z is simply equal to minus Z, so that Z plus minus Z is equal to 0. For example, if Z equal to x comma y, then what is minus Z? It is minus x comma minus y, and it is additive inverse of Z. Let us prove summation of a complex number and its additive inverse. So Z plus in bracket minus Z, it will be equal to x comma y plus minus x comma minus y. In terms of ordered pair, Z and minus Z are written. Now what is their summation? Summation of real parts and summation of imaginary part. That is x minus x comma y minus y. And since x and y are real numbers, so x minus x is equal to 0, y minus y is equal to 0, so 0 comma 0, it is simply equal to 0. So for a number Z, there exists a minus Z, such that Z plus minus Z is equal to 0, and minus Z is called as additive inverse of Z. If Z equal to x comma y, then additive inverse of Z is minus Z, and it is simply equal to minus x comma minus y. And with this, we can define the subtraction of two complex numbers. If Z2 is equal to x2 comma y2, then we can write the additive inverse of Z2 as minus Z2 equal to minus x2 comma minus y2. Now we have Z2, we have Z1 and minus Z2. And what is Z1 minus Z2? That is simply Z1 plus in bracket minus Z2. So Z1 and additive inverse of Z2 are added in this case. So Z1 plus in bracket minus Z2, that is x1 comma y1 plus in bracket minus x2 minus y2. So that is simply equal to x1 minus x2 comma y1 minus y2. It means z1 minus z2 is equal to x1 minus x2 comma y1 minus y2. That means real part of z2, that is x2, is subtracted from real part of x1, real part of z1, that is x1. So x1 minus x2 is real part of z1 minus z2. Similarly, y1 minus y2 is imaginary part of z1 minus z2. So this is the subtraction. Real parts are subtracted and imaginary parts are subtracted. So with this, we conclude today's class. Thank you for your patience. Thank you very much.